Okay, it's 7:10, so I will start with the introduction now. So, good evening, everyone. Myself, Gaurav, coordinator of Isopurple Astronomy Club, and welcome to the third talk session of this semester. Today we have with us Mr. Shaunak Padhyegurjar, and he is a BSMS student of 2019 batch in third year, Department of Physics, and he will be delivering a talk today on binary star systems. And we will have the Q&A session after the talk session, and you can keep posting your questions in the chat box. We will take note of those questions. If there is any doubt you need to ask in between, you can ask it directly. And yeah, the talk does contain a lot some of mathematics as well, so yeah, it will be exciting. Yeah, over to you, Shaunak, now.
Thank you, Gaurav. Hello, everyone. Good evening. This is Shaunak here from third year physics department, and I welcome you all to my talk on binary star systems. Today, I will be talking about binary stars, their importance, types, and evolution. We will be covering almost all basic topics that one might need to know about binary stars. Now, before I start, I would like to say that this talk will require some background knowledge of astronomy, as I have kept the level of the talk slightly above beginner level. But there are some technical concepts in the talk, and maybe some of you may not understand concepts well, but it's completely okay. I'm sure you will guys understand them in future. The recording and slides of the talk will anyway be shared to you later, so you may just revisit the content after some background reading if you wish to. But don't be scared. I will try my best to explain those technical concepts well. Also, I'll drop in a few questions in the talk to keep the talk interactive. You guys may unmute and answer directly, whereas your doubts will be taken care of at the end, just like Gaurav said. Okay, so without further ado, let's get started.
Sorry to interrupt, Shaunak. Basically, guys, whenever Shaunak asks question, just raise your hand. I'll unmute you, and then you can answer the question.
Okay, yes, that's fine. So let's start. So we will start with the definition of binary stars. First, let me ask you a question. What do you guys think when you hear the term binary stars? Any one of you can unmute and answer directly.
Please raise your hands. I'll unmute you. So, Aditya, please.
Binary star is the system of two stars which revolve around the common barycenter.
Yes, that is absolutely correct. So binary stars are basically two stars that are gravitationally bound, and they orbit their common center of mass, or the barycenter. This is very easy to understand, right? I bet all of us have solved mechanics questions in high school involving two stars revolving each other, right? Next, one might ask, what is so special about two stars orbiting each other, and why do we care to study them? Well, your question is completely valid, and it turns out that there is a lot interesting about binary stars. Now, some of you might have heard that more than 50% of the stars in the universe come in binary or multiple star systems. Some estimates even say that about 85% of the stars in the universe come in such systems. So if that is the case, then one would be foolish not to study them at all. Next, also measuring various properties of stars comes with errors, and these errors only increase with increasing distance of stars from the Earth, as it gets more difficult to perform these measurements. However, studying orbits of binary stars helps us to directly determine those properties with greater accuracy. This is all because their motion obeys very predictable and measurable Newtonian mechanics. And as you know, in Newtonian mechanics, all quantities can be measured very accurately. Next, and perhaps the most interesting thing about binary stars is that they can achieve evolutionary states that no single star ever can. We know that stars go through their life, they are born, then then they go through their main sequence phase, then they become red giants, and depending on their initial mass, they die in different ways. So what single stars cannot achieve is that we'll look into this later. Next, so our current theories in stellar astrophysics have been developed on the basis of few stars whose properties have been measured quite accurately. Although few in astronomical terms is still in thousands, but remember that the universe contains trillions of stars. So our sample is quite small to represent such a large population. Thus, we are always seeking more and more accurate data to refine our current theories. And as I said before, binary stars do provide accurate data. And I hope that now you guys are convinced of the importance of binary stars in our current understanding of the stellar astrophysics. Next. Okay, so now let's have a look at some background and terminology required to understand binaries, starting from basic orbital mechanics. I am going to go over this part quite fast because it is very basic. Now, as you can see, almost all binaries have elliptical orbits, and some are more circular and some are more elliptical than others. Depends on the eccentricity. As you guys can see from the diagram, the center of mass lies at the focus of the elliptical orbits of both the stars. And for the forces to balance out correctly, the two stars always need to be on opposite sides of the center of mass at all times, and hence their orbital periods and eccentricities are equal. The semi-major axis of the stars obviously obey this equation, A1 M1 equal to A2 M2, which says that the star with more mass will have smaller semi-major axis, and the lighter star will have the greater semi-major axis. And also, instead of adopting a coordinate system centered at the center of mass, if we choose a coordinate system centered on one of these systems, one of the stars, then the semi-major axis of the orbit of its companion, as seen from the star on which you are sitting on, will be A equal to A1 plus A2. This is quite simple, and all these things are useful in studying orbits of binary stars. And then moving on, we can apply some basic physics to a binary system, and we get to this very familiar equation, p squared equal to a cube p squared upon a cube equal to 4 pi square upon g into m1 plus m2, where m1 and m2 are masses of the two stars. A is the orbital separation, p is the orbital period, and E is the eccentricity. And this is basically the Kepler's third law, which we have already studied, and it is quite easy to understand. So convince yourself with the concept that the orbit of any binary system is completely determined by the masses m1, m2, orbital separation A, orbital period P, and eccentricity E. I hope you are convinced with that. Next, now to study orbit of any binary system, we first need to describe its orientation, shape, size, etc. And to do this, we use a system of parameters called orbital elements. Here we will discuss Keplerian elements, but there are also other kinds of orbital elements, which is a different topic in itself. Now this part is somewhat tricky to understand, so I request all of you to pay a little more attention, as it is of extreme importance in studying binary star orbits. Orbital elements consist of these 6 parameters: eccentricity E, semi-major axis A, angle of inclination I, longitude of ascending node capital omega, argument of periapsis omega, and true anomaly nu. I'll explain all of these parameters one by one. The first two of these orbital elements, that is eccentricity and semi-major axis, describe the shape and size of the orbit respectively. If you think of it carefully, you will understand why this is true, right? Because eccentricity will determine its shape. The eccentricity if it is close to 0, then the shape of the orbit will be close to circular, and if it is greater between 0 and 1, then it will be more or less elliptical. And the size of the orbit will be determined by the semi-major axis, right? So this is pretty easy. Then the next two parameters, angle of inclination and longitude of the ascending node, these two parameters describe the orientation of the orbital plane in the sky. I'll explain this more shortly. And the last two elements, the argument of periapsis describes the position of periapsis, which is the point of closest approach in the binary star's orbit, in the orbital plane. And the true anomaly is basically the position of star in its orbit, and it is similar to orbital phase. So now let's visualize these orbital elements and how they describe an orbit. Also, please remember these names for future reference. So first, let's discuss what are called equatorial coordinates, and which define position of any celestial object on the celestial sphere. There are other coordinate systems as well, but this is the most widely used. Now, first imagine an imaginary sphere with a very large radius, with the Earth or the observer at its center. This is called the celestial sphere. All objects in the sky that you see can be thought of as being projected on the inner surface of this sphere, of the celestial sphere. Or you can also think of the sky as this imaginary sphere, and the celestial bodies as they appear to you in the sky or are on the inner surface of this sphere. And this is, as you may notice, it is a geocentric coordinate system. And I hope you get this concept. Now the position, projection of Earth's equator on the celestial sphere gives us the celestial equator, and the projections of Earth's north and south pole are the north celestial pole and the south celestial pole respectively. Now, just as we describe any position on Earth's surface by latitudes and longitudes, position of any celestial object on the celestial sphere is described by right ascension and declination, or as shortly we call it RA and dec, where declination is analogous to latitudes and right ascension or RA is analogous to longitudes. And just like latitudes, declination is measured from the celestial equator and goes up to 90 degrees, plus 90 degrees on north celestial pole and minus 90 degrees on south celestial pole. Whereas RA is measured from this longitude gamma, just like how longitudes are measured from Greenwich mean time, and Greenwich longitude. And if you ask me what is gamma, then it is the longitude of the sun on the celestial sphere on the day of vernal equinox, that is March equinox. And this longitude is taken to be 0 RA, and it goes on to 360 degrees. However, we usually report right ascension in hours, minutes, and seconds, where 1 hour represents 15 degrees. So 360 degrees, for 360 degrees, we have 24 hours. Now, if you need more info about the celestial coordinates, I request all of you to read up more on equatorial coordinates on your own. As we have limited time, I'll move on And if you don't understand this, we can discuss this in detail at the end if time permits. Coming back to our main topic of orbital elements, consider a binary star's orbit to be arbitrarily oriented as shown in this diagram, where the orbit is represented by this black ellipse. Now, to describe this orbit, we need to define a relative Cartesian coordinate system on the celestial sphere. Now, this line called LOS is called the line of sight of the observer, and it basically connects the observer to the binary star or any celestial object on the celestial sphere. And this blue plane which you can see is a tangential plane to the celestial sphere on the position of the binary star. You may think of this tangent plane as the plane of the sky. For example, if you are somewhere here on the earth and you are looking at some binary star here, then the plane of locally you can imagine the sky as a plane, and that plane is the tangential plane which I am talking about here. Next, we also define a reference direction in this reference plane, and which is and it is tangential to this great circle of longitude on the point of the position of binary star. So I am talking about this reference direction. As you can see, it is tangential to this great circle of longitude at this point. And by convention, we take the direction of this tangent to point towards the north celestial pole. So together, the line of sight, which is this arrow, and the tangential plane, they define the relative Cartesian coordinate system that we were talking about. Now look at the orbit carefully. It intersects this reference plane at 2 points, these 2 points, which are called nodes. Now, by convention, if the binary star is passing from inside the celestial sphere to outside, then the node is called ascending node. And as you can see, in this case, the direction of motion is in this way. So the ascending node in this case is this node, and the opposite node is called the descending node. And if the direction of motion was like this, then this would become the ascending node and this would become the descending node. I hope you are understanding all of this. Now notice that the angle between this reference plane and the orbital plane is the angle of inclination I, right? I will move on to the next slide so that you can visualize this better. Sorry, it's not, yeah, sorry for that. You can see here that this gray plane is the reference plane we were talking about, and this red arrow is the reference direction, and this yellow plane is the plane of the orbit. Now you can clearly see that the angle between the reference plane and the orbital plane is this angle of inclination I. Next, the longitude of ascending node, capital omega, is shown here in green, and it is the angle between the reference direction and the ascending node here. So, and it is measured anti-clockwise. So if you imagine a line connecting the ascending and descending nodes, then we can measure an angle from the reference direction towards the ascending node, and that is basically the longitude of ascending node. Now, if you think carefully, angle of inclination and longitude of ascending node define the orientation of orbital plane. For example, if this orbital plane, which is the yellow plane, was lying in the reference plane, and if I incline it by some angle of inclination I, then the orbital plane will be oriented by some angle to the with respect to the reference plane. After that, we can rotate the orbital plane by keeping the angle of inclination constant about this axis perpendicular to the reference plane, and that will basically orient the orbital plane in different ways. So the angle of inclination I and the longitude of ascending node capital omega describe the orientation of the orbital plane in the on the celestial sphere. Next, we also require another parameter called argument of periapsis, that is nu, to describe the position of the periapsis in the within the orbital plane. And if you see the argument of periapsis is measured from the ascending node, which is this purple angle denoted by small omega. This is the argument of periapsis. And as I said, periapsis is basically the point of closest approach of the binary star in its orbit. Perhaps you can visualize it better in this diagram on the right. This is the orbit which we were talking about, and this plane is its orbital plane. Now, this is the ascending node here, the point of intersection, which is the n, and this is the longitude of ascending node. And from this, we measure the small omega, that is argument of periapsis, and this is the point of periapsis. So depending on different values of omega, small omega, the tip of the ellipse or the argument of periapsis will move in this orbital plane. I hope you got the concept of argument of periapsis and all the orbital elements. And the last orbital element is the true anomaly nu, which basically describes the orbital phase. So if the binary star is moving in its orbit like this, then only the parameter nu will change, and it is taken to be 0 at the point of periapsis, and it basically goes on up to 2 pi. And this is the only parameter that changes with time, while all other parameters are constant. However, for very long periods of time, over very long periods of time, the other orbital elements may change due to the change in orbit itself. And so basically, this completes our discussion on orbital mechanics. And now let's move on to some more terminology. Now, obviously, a binary star system consists of two stars, right? But while studying them, how will you tell them apart? So this is the convention of naming them. We generally refer to the generally refer to the brighter of the two as primary, while the other one is secondary. However, keep in mind that primary need not be the more massive star of the two. Also, we sometimes refer to the components as hot and cold, where obviously the component having greater temperature is the hot component and the other one is cold. So this is some terminology. Next, now let's have a look at few things which frequently pop up in study of binaries. In a type of binaries called eclipsing binaries, their brightness varies over time. We will look into the types of binaries shortly, but just first let's look at this term. So a plot of brightness against time, or better against orbital phase, is called a light curve. As you can see in this diagram, the brightness of the system is changing periodically with dips, regular dips occurring at certain intervals of time. And so basically this plot of brightness against the time or orbital phase is called light curve. Next, we have what is called radial velocity. Now let's say in a heliocentric reference frame, that is a reference frame that is centered on the sun, a far away object in space or any celestial body outside the solar system has some velocity in some arbitrary direction like this. And we can always split the velocity vector into two components, one which is parallel to the line of sight of the observer and one which is perpendicular to it, right? So if you imagine, if this is the sun and it is the, and we have a heliocentric coordinate system, and we have an object here somewhere in space, and it has some velocity vector, but while looking at it from the coordinate system, and here is the plane of the sky, then we will have then we can split this velocity vector into two components, one which is parallel to the line of sight and one which is perpendicular to the line of sight. And the velocity vector which is parallel to the line of sight is basically called the radial velocity of that object, and the component perpendicular to the line of sight is called the transverse velocity. And this transverse velocity basically gives rise to what is called proper motion. A proper motion of the object is this transverse velocity will cause the object to move across the plane of the sky, and this motion is called proper motion of the object, and it depends on the distance d of the object from the observer. For very far away objects, proper motion is too small to detect, and also by convention, positive radial velocity means that the object is receding from the observer, and negative radial velocity means that the object is approaching the observer. And also one thing, radial velocity is measured in usually measured in kilometers per second, and proper motion is measured in milliarc seconds per year. Next, we have a plot of radial velocity against time, which we call a velocity curve. In case of binary stars, as you may have probably guessed, that the radial velocity of components changes periodically with time, and which gives rise to this sort of wavy sort of curve, velocity curve, as it is shown here. So basically, velocity curve is just a plot of radial velocity against time, nothing much special in that. Okay, so now we are done discussing background and terminology. Now, before we move on to the types of binaries, let's first look at what are not binaries. Now, there are thousands of stars in the night sky, so there is an appreciable chance that two stars that are very close to one another may look like a binary pair, right? But that doesn't mean that they are gravitationally bound to form a binary system. Such stars are called optical doubles. Their apparent position in the sky on the celestial sphere just happens to be along a similar line of sight and nothing more than that. This diagram very well sums up this idea. As you can see from the Earth's point of view, they appear to be very close together, but from a distant perspective, we see that the stars are very far apart and are not gravitationally bound. So optical doubles are not binary stars in real sense. Okay, so now let's see what are the different types of binaries. Typically, binaries are classified on the basis of mode of observation, that is how we observe them or how we detect them. So we have these four kinds of binaries: visual binaries that are detected through images or telescopes, or basically optically. Then eclipsing binaries that are detected photometrically, that is by studying the changes in their brightness. Spectroscopic binaries that are detected through spectroscopy, and astrometric binaries that are detected by astrometry. That is precise, and astrometry means precise measurement of position and movements of celestial objects. So let's look at each one of these types one by one. The first type is visual binaries. Visual binaries are those in which both components are visible and can be resolved by a telescope. For example, Mizar, located in the arm of the Big Dipper, and Sirius, which is the brightest star in the night sky. Uh, Detecting visual binaries involves measuring position of the secondary with respect to the primary multiple times over the time, and we plot the most probable orbit after sufficient observations have been done, as you can see in this diagram. uh, from the perspective of the primary, this we have plotted this orbit by taking measurements of the position of the secondary over uh, over the time. However, visual binaries are characterized by very large orbital separation, and hence their orbital periods also are very large, and they can range anywhere from between few years to even hundreds or thousands of years. And due to this, very few visual binaries are detected. As as you may have probably guessed, that the observations, first of all, the observations requires many years of accurate measurements, and also the motion is not very detectable if the binary is situated very far away from the Earth. So as you can see, these two examples, this is the orbit of Sirius B around Sirius A. Sirius B is a white dwarf, and Sirius A is an A-type star around 2 times the mass of the Sun. And Sirius has a period of around 50 years. And in the second example of 70 Ophiuchi, the period of the binary is about 87.7 years. So you can probably guess that detecting visual binaries is a very tedious task, and that's why we detect only a few of them. Thus, the determination of orbit takes years due to large orbital periods involved. But once the orbit is determined, we can solve for the orbital elements, and we can also find out their stellar parameters like mass, radius, density of the star components, etc. And we usually follow this flow chart to determine the orbit and other stellar parameters. First, we take position measurements for several years and then plot the positions. Then we calculate the distance to the system by other methods, and which in turn helps to determine the size of the orbit. Next, we find the true orbit, because any orbit is basically a projection of the real orbit in the night sky. So we, by some methods, we determine the true orbit, and then by some analysis, we determine their orbital elements. Now we can, and then using the Kepler's law, we can find the masses of the components, and by using by using mass luminosity relation, we can find luminosity, and subsequently we can find other parameters as well. However, this method involves very large error margins, as it depends on accurate distance and position measurements, which are obviously difficult in astronomy. And so these kind of binaries are not very helpful. Then we have eclipsing binaries. So in eclipsing binaries, the line of sight of the observer lies in the orbital plane of the components, which means that we are looking at the system edge on. For example, if this is an observer and this is the plane of the sky, then we are basically viewing the orbital plane like this. So that is why we see the component stars to move in a straight line over the time. So, and this basically corresponds to angle of inclination I equal to 90 degrees. So before we proceed, here is a question for you. Can any one of you tell me why does the angle of inclination equal to 90 degrees correspond to the system when as it appears oriented edge on from Earth? Let me repeat the question. Why does the angle of inclination equal 90 degrees correspond to the system to appear oriented edge on from the Earth? Let me give a hint by showing you the diagram for orbital elements again. I guess you can find out why this is the case from this diagram. Just focus on this tangential plane and the orbital plane. You may unmute and answer or raise the hand. Yes, go on.
So if it is in our line of our sight, then it must be perpendicular to the tangential. The plane of orbit will be perpendicular to the tangential plane.
Yes, perfect.
That's why it will be 90 degree. No?
Yes, yes. Right. So let's get back to our main discussion. And as you may have probably seen in this diagram, since both the stars in orbit in a plane which is viewed edge on from the observer's perspective, so we see mutual eclipses when one of the star passes in front of the other, which blocks the light coming from its companion. Thus, we see a drop in total brightness of the system, as you can see in this diagram. And when the dimmer star eclipses the primary star, the brighter star, the dip in brightness is larger than when the brighter star eclipses the dimmer star. Also, the deeper of the two eclipses is called primary eclipse. Primary eclipse, regardless of which star is being occulted. Typically, occultation of hotter component causes primary eclipse, and also eclipsing binaries are kind of variable stars, not because the individual components are variable in brightness, but due to their eclipses. Then, thus, the light curves of binaries are typically characterized by periods of practically constant magnitude, and with periodic drops in intensity when eclipses occur. Now, eclipses can occur once or twice during a period of during one orbital period, as some eclipses might not be detectable. Usually, secondary eclipses are sometimes not detectable. Now we can determine the period of the binary from its light curve. Obviously, we can see that the period between the two primary eclipses or two secondary eclipses gives us the orbital period of the binary. And by analyzing the light curve, we can also obtain other orbital elements, by analyzing the light curve, we can obviously obtain the orbital period and some orbital elements, but not all. And if radial velocities of the binaries are also known, then we can obtain the ratio of radii of the two components also. So we can determine the relative size of the two components. However, just by analyzing the light curves, we cannot extract all the desired information like stellar masses and etc. from the light curve alone. Then examples of eclipsing binaries include Algol, Beta Lyrae, Epsilon Aurigae, etc. You might not have heard these names before. Next, eclipsing binaries are further divided into subtypes depending on characteristics of light curves. These subtypes are EA, EB, and EW. I'll quickly go through this section as it is not very important. The EA type eclipsing binaries are similar to Algol and are characterized by well-defined eclipses. The components are spherical or ellipsoidal. The brightness can dip by several magnitudes during the primary eclipse, and secondary eclipse may not be visible, sometimes detectable. Now you can see this is this diagram over here, the first one of these. This is a typical light curve of an Algol type eclipsing binary. As you can see, the eclipses are well defined, and we can easily determine the beginning and end of eclipses. The next type is EB type, which is beta Lyrae type. This type is characterized by massive and ellipsoidal components, which are very close to each other. And because of their closeness, and due to their tidal forces, their shape becomes somewhat elliptical, ellipsoidal, like an egg shape. And that is why their brightness changes continuously during orbital period. Hence, it is impossible to predict the beginning and end of eclipses accurately. As you can see from this light curve of EB type eclipsing binaries, the brightness of the system changes continuously, and we cannot properly define the beginning and end of eclipses. And this effect occurs because they are ellipsoidal in shape, and as they are so close to each other, the light from one component is reflected off the surface of the other component, and that is why during the various points of time in orbit, the brightness changes continuously. And this reflection is because the light is absorbed and then re-emitted, or because of scattering of light on the surface of the companion. And the last type is the EW type. And these types of eclipsing binaries are characterized by continuous change in brightness and nearly identical dips in brightness, as you can see from this last diagram here. And this is because the components are in contact with each other, and hence their temperatures are also almost equal. And that is why both of the eclipses produce almost same equal dip in brightness. Now here is a short animation that I have made of eclipsing binary called Algol. Let's have a look at it. As you can see from these two stars, they are orbiting in one plane as seen from the observer's perspective. And when the dimmer star eclipses the brighter star, we see a larger dip in brightness. Whereas when the brighter star eclipses the dimmer star, we see only a short dip in brightness. And in some cases, this shorter eclipse or the secondary eclipse is not even detectable. Okay, so getting back to our main content. Hope you like the animation. Moving on, next type of binaries are spectroscopic binaries. These binaries cannot be resolved by a telescope, and their binary nature is revealed only through the study of their spectrum. These, personally, I feel these kind of binaries are the most interesting. Now, think carefully that unless the orbital plane of the binary is perpendicular to the observer's line of sight, at almost all points of time in the orbit, one star will be approaching towards the observer, and while the other star will be receding like this. And after some time, the process is reversed. That is, the other star will start approaching, and the first star will start receding. And due to this, during the orbital motion, the light of the stars that we receive will get red shifted, then blue shifted, and then again red shifted as they move away or towards towards us due to Doppler effect. Also, spectroscopic binaries are typically characterized by small orbital separation, and that's why they have they have faster orbital velocities and smaller orbital periods. And since we only have the information of the spectrum, we can measure only radial velocities, and their velocity curves give the information about their orbit. This is a very important point to remember, that we only have the velocity curve data, and that's all. And this is the formula to find radial velocity at any particular point. V equal to c times lambda minus lambda naught by lambda naught, where c is obviously the speed of light, lambda is the observed wavelength, and lambda naught is the lab wavelength, or the wavelength in stationary frame of reference. Okay, so here is what a typical velocity curve looks like, and here in this diagram we see periodic shifts in wavelength of light of both stars. Have a look at it carefully and you will understand the concept easily. And this is notice that the whole graph in this case is shifted along the y-axis, and this is because the center of mass is the velocity, radial velocity of center of mass is also contributing to the total radial velocity, and this can the velocity of radial center of mass can be positive or negative depending on different cases. Now remember that depending on whether we detect spectral lines of one or both components, spectroscopic binaries are classified as SB1 type and SB2 type respectively. Now the general equation for velocity curve is given as this formula over here. V rad equal to k times cos of nu plus omega plus E times cos omega plus gamma, where 2 pi k is equal to 2 pi a sin I upon p into 1 minus e squared, which can also be simplified as V max minus V min by 2. So basically k is the amplitude of this oscillation of the radial velocity. It is called a semi-amplitude, and gamma is the velocity of center of mass, or the systemic radial velocity. And as you may notice in this formula, we have nu and omega here, where omega is the argument of periapsis and nu is the orbital phase or the true anomaly. Now it turns out that we cannot determine separately I, that is angle of inclination, or the semi-major axis from analysis of radial velocity curve alone. We can only find their product, that is a sin I. Hence we can only find an upper limit on masses, which is given by this mass function. Fm is equal to m1 cube sin I cube upon m1 plus m2 whole square, which can also be written like this. And for mass m2, we can just interchange the subscripts 1 and 2. Now, why I'm saying that the mass function gives an upper limit on the masses is because the sine cube I will range from 0 to 1, right? We don't take negative values or just take a mod of it. It doesn't make any sense. It doesn't make any difference. So for some value of m1, if we set the angle of inclination to 90 degrees, then this term will become 1, and thus we get an upper limit on the mass of the component, while for other values of inclination it will obviously be less than that. So in case of SB2 type binaries, since we know, since we can measure the radial velocities of both stars using this formula and taking the ratio of m1, upper limits of m1 and m2, at best we can get only the ratio of masses m1 upon m2 for SB2 type. While in case of SB1 type, since we know the radial velocity of we can measure the velocity curve of only one star, we are stuck at only the upper limit of only one component. And sorry, we can measure mass of one component by other methods, and we can know only an upper limit on the mass of the second component. So that is it. And so if you may notice that eclipsing binaries and spectroscopic binaries by themselves cannot determine all the parameters that we are interested in. We can only find some of the orbital elements, and only at best we can measure only ratio of masses or only an upper limit to the masses. We cannot exactly determine the masses and other stellar parameters. So the best kind, so we usually apply other techniques which are employed in visual binaries or other kinds of binaries to determine all the parameters. So basically for any given binary, we usually do the observations in both ways. Like visual binaries also, for example, if a spectroscopic binary is also a visual binary, then we can determine I from the orbital analysis, and hence we can calculate the masses of the spectroscopic binaries by you plugging in the value of exactly I exactly. And so like this, we can also employ the analysis of eclipsing binaries for in the analysis of spectroscopic binaries. The best kinds of binaries are those which are both eclipsing binaries as well as spectroscopic binaries. As we know that in case of eclipsing binaries, angle of inclination is 0 or very close to 0. We can easily determine I, and hence the masses of their components as well as other stellar parameters can be exactly computed. And these 2 points apply for eclipsing binaries too. And that's it. That's all. And this is the reason why I was telling that and binaries, the study of binary systems provides accurate determination of masses and other stellar parameters, while in case of single stars, the methods employed are not so accurate, at least for very distant stars. And finally, the examples of spectroscopic binaries are Mizar A and Mizar B. We will look at an image of this at the end. And here is again here is an animation of spectroscopic binaries that I have made. So as you can see, for any random orientation of this orbital plane, the spectral lines will oscillate among their mean position as during different points of time in the orbit, and hence by study of the spectrum of eclipsing spectroscopic binaries, we can reveal their eclipsing binary nature. So basically, we take spectroscopic measurements at different points of time and measure the shifted wavelengths, and from that we compute the radial velocities and do the further analysis. Then the last kind of binaries are the astrometric binaries. In this kind of binaries, only one component, that is the primary, is visible, and its proper motion is found to wobble around about a straight line in the sky. So in the night sky, over long periods of time, we find that the visible component is wobbling around a straight line. And this sounds strange, right? The wobble is the result of the visible component being in orbital motion of around the invisible secondary component. The secondary is not visible because it may be very dim or masked by the glare of the primary, or it may also be an evolved star like a white dwarf or a neutron star, both of which emit very less visible light. Then, for those of you who know what parallax is, might argue that the wobble may be due to parallax effect. But the answer is obviously no, because proper motion is always calculated by subtracting the parallax effect. And also, astrometric binaries are difficult to detect, as long and accurate measurements of proper motion is difficult, and proper motion is not detectable for very far away objects as well. So and since we can these kinds of binaries are similar to visual binaries, one might expect that the same physics as that for visual binaries can be applied to astrometric binaries too, to determine the orbital elements and masses of the components and other stellar parameters. And examples of astrometric binaries include Sirius and Procyon. Sirius is in a binary pair with a white dwarf, as well as Procyon is also in binary pair with a white dwarf. And since white dwarfs emit very less visible light, they are usually masked by the glare of the primary component. So that is why they are not visible. And this diagram will help you visualize better. As you can see, the visible component follows the wobbly path around a straight line in the sky, and from that we deduce how the secondary will move and determine the orbital elements and other parameters. So here again is an animation of astrometric binaries.
Hi, Shaunak.
Yes.
Sorry for the disturbance. We have passed 1 hour. So if possible, can you please wrap up fast?
Yes, sure.
Thank you.
So see in this animation that the star is wobbling in the night sky around a straight line, and this is the expected proper motion. If this were a single star, then it would just simply move in a straight line. But as this is in orbital motion with its secondary, the proper motion wobbles around a straight line. So that is what are astrometric binaries. And these are one special kind of binaries called cataclysmic variables and X-ray binaries. Basically, in these kind of binaries, one of the components is a white dwarf or neutron star or a black hole, and the other component is transferring its matter towards the the compact object, that is white dwarf, neutron star or black hole, and because of the accreting matter, these binaries tend to be very energetic, tend to emit very energetic radiation like X-rays and etc. And basically the distinction between cataclysmic variables and X-ray binaries is that cataclysmic variables include a white dwarf, whereas X-ray binaries have a neutron star or black hole as one of their components. Let's just skip this part. Then we have what are called closed binaries. As the name suggests, in closed binaries are those in which the orbital separation between the components is very less, and to the extent that the components can actually influence the evolution of each other. And to explain this part, we define what are called Roche lobes. Roche lobe is a region around a star in a binary system which or within which the orbit material of that star is gravitationally bound. For example, basically it's the region of influence of that star. You can see the shape of the Roche lobes is teardrop shaped, and they are connected tip to tip at this first Lagrange point. Um, so the any matter which is inside one of the star's Roche lobe will be gravitationally bound to that star, and if it gets out of that star's Roche lobe, then it will be attracted towards the other star. So now let's see why in some binaries we observe mass transfer. So as you may know that after exiting main sequence, the stars enter the red giant phase and they expand quite a bit. Actually, they expand very greatly. And in that scenario, if they are also closed binaries, then as the star expands, its matter may get out of its Roche lobe, and that's why it will be attracted towards the other star, and the mass transfer occurs via the first Lagrange point, that is L1. Now, as the mass is lost by that star, its Roche lobe will shrink, and which may or may not stop the mass transfer depending on the mass of that binary star. Here is an animation which will help visualize it better. See, these two stars are orbiting very close to each other, and as this star exits the main sequence to enter the red giant phase, it will flow, its matter will flow, get out of the Roche lobe, and it will start moving towards the other star, and it will form an accretion disk. Now, depending on the initial mass of this donor star, it may end up as a white dwarf or neutron star or a black hole. And basically, because this star has gained more mass, it shortens its lifespan, because you may know that heavier stars live shorter. And after some time, the star which had first received matter from the first this donor star, after it evolves off its main sequence, it may also grow in it will grow into the red giant phase, and it may also start mass transfer. And this time, because the original star is a white dwarf or a compact object, if the white dwarf exceeds the Chandrasekhar mass limit of 1.44 solar masses, then it may result in a supernova explosion of type 1a. Now, this is what is mass transfer, and based on the Roche model, we can also classify binary stars in these three classes: detached binaries, in which both components are well within their respective spheres of influence or Roche lobes, as you can see in this diagram. Then there are semi-detached binaries, in which one of the stars fills its Roche lobe and transfers its mass to the other, as we just saw in the animation. And the last kind is contact binaries, in which both stars fill their Roche lobe and start the mass transfer. So this basically forms a Circum binary envelope around them, and the two stars may merge together or may evolve as contact binaries later on. Now, so far we talked about we haven't talked about formation of binaries, so let's quickly go through this. Binary stars may follow these three, or there are even more processes of formation, but these three are well understood. First is gravitational capture. This scenario is highly unlikely, because actually, if you think if two stars are moving in some random direction, and if they by chance happen to come close to each other, then they cannot form a stable orbit, because their initial kinetic energies, the sum of their initial kinetic energy is greater than the total energy of the binary pair. So the conservation of energy basically rules out the formation of binaries by this process. Actually, one more star is required or to take away the excess kinetic energy, or it may so happen that if they approach very close to each other, then due to the tidal forces may take away the excess kinetic energy, and it may form a binary star. The other process, which is more plausible and which is more widely acceptable, is that the two stars are formed from the same cloud of dust and gas, and during their formation the cloud somehow splits into two parts, and then they form as separate protostars, and then they uh, come into orbit of each other. And the third process is a three-body problem or n-body problem. In this, a system of stars having three or more stars having comparable masses can form a binary. As you may know that the three-body problem or n-body problem is chaotic, and eventually all the stars will the system until only two stars remain, and that is how we obtain a binary star system. Now, yeah, let's talk about the evolution again. Now, in case of visual binaries, as you remember, the two components are very far apart. That is why those two stars will evolve as regular as single stars, and that is why their evolution is not much very interesting to discuss about. They will form, then they will continue burning their hydrogen in the main sequence, then exit the main sequence, become red giant, and depending on the initial mass they will die in different manners. So that is that. Then what we discussed previously in case of mass transfer was the case of evolution of closed binaries, and in this case a very wide range of possibilities are there. After the formation, for initial years in their life, the two closed binaries will continue to evolve peacefully, unless one of the stars exits the main sequence, expands, fills its rose lobe, starts mass transfer, and then ends up as white dwarf or neutron star or black hole. And that basically shortens the life of the receiving star. And as you saw in that animation, it may start mass transfer again, which may cause supernova explosion, or it may just blow up to form another neutron star or white dwarf. Then this is the case which we saw just now in that animation. So here we have a interesting paradox called Algol's paradox. In some binaries, the massive component is still in the main sequence, while the less massive component is an evolved star, like the white dwarf, right? And the solution to this paradox is pretty easy. It is basically the same scenario as we witnessed before. The secondary star, less massive component, is an evolved star because it has already transferred it has already evolved off the main sequence and transferred its mass to the previously less massive star, and now that is why the receiving star is more massive of the two. And one more case in this is that the components have similar masses. In this case, both the components will more or less exit the main sequence at equal times, and that is why both of them will fill their Roche robes more or less during the same time and form a contact binary. Now this contact binary may merge due to some factors, or sometimes may evolve as a closed binary, and the stars may later form white dwarfs or a pair of neutron stars or even a pair of black holes depending on their initial masses. So that is how we end up with a pair of white dwarfs and a pair of neutron stars and pair of black holes. Now, as you may have probably guessed, the binary stars are responsible in some cases for very high energy events like supernova or even gamma ray bursts. So if one of the components is a white dwarf and if it is in close orbit with a main sequence star, then the main sequence component may overflow its rho slope after main sequence and start mass transfer. And if that accreting white dwarf exceeds the Chandrasekhar mass limit of 1.44 solar masses, then it will cause a type 1a supernova explosion, like we saw in that first animation, in the mass transfer animation. Whereas if one of the components is a neutron star or black hole, then the accretion disk will be very hot due to the extreme conditions, and it can form X-ray binary. For example, Cygnus X1. This is a very famous example, and it contains one of the first black holes ever detected. And finally, a binary star system may end up as a pair of neutron stars in close orbit, which will eventually lead to orbital decay due to emission of gravitational waves, and the two neutron stars may eventually merge, giving rise to a kilonova explosion, and which is also accompanied by a short gamma ray burst. So binary star systems are also responsible for some of the most energetic events in the universe. And finally, we have come to an end of this talk, and let's have a look again at some examples. This is the famous Alcor-Mizar system in the arm of the Big Dipper constellation. As you can see, Alcor and Mizar are very close to each other, but it is not confirmed whether they are gravitationally bound or not. So basically, we treat them as optical double. And if you zoom in or if you look through a telescope, you will see that Mizar is actually composed of two stars, Mizar A and Mizar B, and they form a visual binary because we see them through a telescope. And if we perform spectroscopic analysis on Mizar A and Mizar B, then we will actually find out that Mizar A and Mizar B are each a pair of spectroscopic binaries. So Mizar is actually a system of 4 stars, and spectroscopic study of Alcor also reveals that it is a spectroscopic binary. So in all, this example covers almost all types of binaries. It is an all-in-one example. And this is the picture of Sirius A, this bright star over here, and this tiny little dot here is the Sirius B, which is a white dwarf. And this is a visual or astrometric binary. Actually, first it was discovered as an astrometric binary, but due to advancements in telescope, we finally can resolve these two components. And finally, this is an example of Cygnus X1, which I told you about just a minute ago. In this is a black hole which is accreting accreting mass from blue supergiant, and it is emitting very high energy X-rays. Yeah, so in X-ray images reveal the jets of the black hole as well. So this is an example of X-ray binary, and that's all. Thank you for listening to my talk. And I hope that all of you learned something from this and enjoyed the talk. And I hope that my boring and monotonous voice didn't make you feel sleepy. So now if you guys have any questions, we can take them up.
Yeah, please, guys, please raise your hands and I'll unmute you guys, and then you can ask the question. Till that time, there are some questions in the chat box. I'll put them like in the chat box by compiling them. Is that okay?
Yes.
Shaunak, can you see the questions in the chat box? Shaunak? Priyanshu, it will be nice if you like unmute and ask a question.
So I was asking why most of the stars are binary. Any possible explanation have been given? If
So I believe this is the first question, right? In the radial velocity plot, what was the origin?
No, can you please answer Priyanshu's question first? He asked you right now.
Why most of the stars are binary? Any theory? Yeah, so basically there is no such theory that has been proposed. Basically, stars, since you may be knowing that stars are formed out of gas and enormous clouds of dust and gas, which are called molecular clouds, and many a times it happens that the molecular cloud is so huge that it actually fragments into multiple parts, and each part then forms a separate star. And since they are located in such close vicinity, they form multiple star systems. And if there are more than two stars, then the problem enters the realm of n body problem. And any system containing more than three stars of comparable masses have actually that system behaves very chaotically. It is very dependent on the initial conditions, and over the time most of the stars in that system will be thrown away out of the system until only two stars remain, which form a binary pair. So uh, that is how multiple star systems or binary systems are formed. Actually, I have linked two papers in the references. Please do check it out on formation of binaries. In this, they have discussed many processes by which the multiple star systems or binaries are formed. So after you receive the slides of this talk, please go through these papers. And if you want to discuss anything about them, you may please contact me via WhatsApp on this number, or which is preferable, or via email. Then
thank you. I've taken a screenshot.
Rohit has a question. Rohit, can you please unmute yourself and ask a question?
It's okay, I can read it from the chat. I believe this is the question, right? Can you share your views on planet systems around binary stars? Right? Yeah, so basically it all depends upon the masses of the binary stars and mass of the planet itself. If the mass of planet is a significant fraction of the mass of binaries, then that system goes into the realm of three body problem, and it may happen that the star will get the planet will get ejected out of the system. But also around some binaries we find planetary systems. Basically there are as far as I remember, there are two kinds of planetary systems around binaries. One is that in one type is that in which the two binary the two components in the binary star are revolving around each other, and one of the star hosts certain planets. Also, it may so happen that in the other type, that the planet is actually revolving around the whole system. That is called a circumbinary planet. As I will better describe the scenario as like this, that the two components are revolving around each other, and around that whole system, one planet or multiple planets can be revolving. So I think these are only the two stable configurations that we can find in the universe. Rest all, I think, become chaotic, and then some planets may get thrown out of the system. And I believe there is one more question from Rohit. Which application do you use for the animations? So I have made the animations in Blender. It is a 3D animation software, if you know.
Shaunak, now you can take those questions.
Okay, so in the radial velocity plot, what was the origin? So let me get back to that plot. Yeah. So basically in radial velocity, we plot radial velocity against orbital phase, right? So 0 basically corresponds to the point at which we start observing the binary system. We can take it as the orbital phase 0, and then we proceed as we proceed in time. We have other phase orbital phases, and orbital phase usually lies in 0 to 1 range, because orbital phase is basically time of observation divided by orbital period. In this case, that in this velocity curve, the time is reported in days, or sorry, basically the x-axis is corresponding to time, but we usually don't plot velocity curve with respect to time. It is usually in most cases we plot it against orbital phase only, because time, for some reasons which I am not discussing right now, time is not a great parameter to plot against. Then there is one other question. Every binary system can be eclipsing if viewed from side. Yes, every binary system can be eclipsing if viewed from side, but in this case, we are talking about only the case when we are observing it from Earth, because we are not going anywhere in the universe to see that binary, right? All that matters is how the system looks from the Earth's perspective, or from the observer's perspective. So it is basically a matter of chance. If the orbital plane is such that it is looking edge on from the observer on Earth, then you will see it as eclipsing binary. But if you are suppose on any other planet, or in any other system in the galaxy, then you may see it as in different orientation as well. So it's just a matter of chance that the orbital plane aligns with our line of sight. And then what causes the nebula to form two or more multiple protostars? So for that, I will recommend that you please go through this paper, which I have listed here. Both of these papers contain wonderful explanations for how the fragmentation of the molecular cloud occurs. If you have any doubts, then feel free to contact me for further discussions. So are there any other questions? You may unmute and ask directly if you want to. I guess most of them have left now.
Yeah.
There are
Yeah. So I guess there are. Does anyone want to ask any questions? Please raise your hand. I don't think so there are any questions, Shaunak. So I think we will wrap this up. Thank you, everyone. Thank you, Shaunak, so much. That was really an interesting talk. Though I didn't felt it monotonous at all. It was like very detailed about binary star systems. So